This is the topic for today, positive linear maps. We begin with notation, preliminaries, and some properties of positive definite matrices. We discuss only those properties which we are going to use here. So we start with definition of Hermitian matrix. A square matrix is Hermitian if A equal its conjugate transpose. Equivalently, AJI is equal to AIJ conjugate. The diagonal entries and eigenvalues of Hermitian matrices are all real that we have studied. The inverse of a Hermitian matrix, if it exists, is also Hermitian. Sum of two matrices is Hermitian, and the product of two matrices is Hermitian if and only if these two matrices commute. Now this first theorem, let A belongs to Mn. Then A is Hermitian if and only if x star Ax is real for all x belongs to Cn. This we have studied in numerical range. X star Ax is real, then A is Hermitian matrix. Proof we have already studied. Now definition of positive definite matrix. Let A be a square matrix if x star Ax is strictly greater than 0 for all x belongs to Cn and x not equal to 0 vector. Then A is positive definite. And if x star Ax is greater than or equal to 0, then A is said to be positive semi-definite. And we denote it by PSD and positive definite by PD. Now x star Ax is greater than or equal to 0 means if for some x this equal to 0, then it is positive semi-definite. For example, consider this matrix 2 by 2 matrix 1 1 1 1. This is positive semi-definite but not positive definite. Why? If we take x2 with this vector x not equal to 0, then we calculate x star Ax, and this comes out to be, after calculation, mod x1 plus x2 whole square. So if we take x2 is equal to minus x1 here, x2 is equal to minus x1, then this becomes 0 and x is not equal to 0. For example, if we take x1 to be 1, x to be minus 1, we get this value 0. So this matrix is positive semi-definite and not positive definite. Now this matrix, this simple example, diagonal matrix, unit matrix, this is positive definite. Again, we can show this by using definition. X star Ax we calculate from here, and this comes out to be mod x1 square plus mod x2 square. Now when x is not equal to 0, then either x1 or x2 is not equal to 0. So this is always strictly greater than 0. So this matrix is positive definite. Now this exercise, if Aij is a square matrix and is positive definite, then A conjugate, A transpose, A star, and A inverse are all positive definite. Take A to be positive definite, then A star is equal to A, because A is Hermitian matrix. Whenever we have positive definite matrix, this means first it is Hermitian. Why? X star Ax is strictly greater than 0 means x star Ax is real. And when x star Ax is real, then matrix is also Hermitian. So A star is equal to A and x star Ax is strictly greater than 0 for all x belongs to Cn. X is not a 0 vector. Now we have A star is equal to A, that is A conjugate transpose is equal to A. And we can write this as A transpose conjugate this is equal to A. Now taking conjugate both sides, we have A transpose is equal to A conjugate. So we can also take this as definition of Hermitian matrix. A transpose is equal to A conjugate. Now for any x belongs to Cn, x star ATX. Now we are showing this AT and A conjugate both are equal. They are also positive definite. This equal x star A conjugate x because A transpose is same as A conjugate. And since this is a number, we can take its transpose also. Both are equal. Now this equal x transpose and then A conjugate transpose, which is A star, and then x star. X star mean x conjugate transpose. So this remains only x conjugate. Now take this x star to be y. And then y star become x transpose. That is, this is x star, this is y, this is y star. And A transpose is same as A because A is Hermitian. Now A is positive definite, so this is going to be greater than, strictly greater than 0. So A transpose and A conjugate are then also positive definite. Now if A is positive definite, it is also Hermitian. So A star is equal to A, hence A star is also positive definite. Now we show inverse is also positive definite. If inverse exists, we have this equation A inverse is equal to identity. Now take star conjugate transpose both sides. This I star is I and conjugate transpose of this is A inverse star A star. Now this A star is A because A is positive definite, therefore it is Hermitian. Now if we have this equation x y is equal to identity, this means y inverse is x. So this means A inverse is A inverse star. So this shows that A inverse is also Hermitian. Now x star A inverse x, we show now this positivity. This can be written as x star A inverse A because this is identity, then A inverse x. And now put A inverse x is equal to y. Then calculate y star, this comes out to be x star A inverse star. And we have shown that this is Hermitian. So this equal x star A inverse. So this can be written as y star A y, where y is a non-zero vector in Cn. And since A is positive definite, this is strictly greater than 0. So A inverse is also positive definite. Show that the main diagonal entry, this is simple exercise. The main diagonal entries of a positive definite matrix are positive. And if it is positive semi-definite, then we can say that the diagonal entries are non-negative. X star Ax is strictly greater than 0. We take x to be this column vector, 1 at kth position, and all other entries are 0. Then x star Ax is equal to Akk. Therefore, Akk is greater than 0 when A is positive definite, and it is true for all k1 to up to n. Also, we can use argument of numerical range. If A is positive definite, its numerical range is in right half plane on x-axis, real axis. And we have also shown that diagonal entries are also in right half plane. So diagonal entries are also positive if A is positive definite. Now next theorem, let A be a square matrix of order n. Then A is positive definite if and only if x star Ax is positive definite for all x belongs to n. First, this part is simple. If x star Ax is positive definite for all x belongs to Mn, then we can choose this x to be identity matrix. And then this becomes only A. So if this is positive semi-definite, then A is also positive semi-definite. Now converse part, if A is positive semi-definite, then X star AX is also positive semi-definite. Let A be positive semi-definite, then this is greater than or equal to 0 for all X belongs to Cn. Belongs to C. Then X star X, write this matrix X star AX X. Now put XX is equal to Y, then this, that is a column vector, and X star X becomes Y star. So this is positive semi-definite. Positive semi-definite. Note that if we take A positive definite and X singular, then X star is positive definite. Am I audible? Here it is showing connection is unstable internet.
Yes, sir. Yes, sir.
Now next theorem, let A belonging to Mn be Hermitian. If A is positive definite, then all its principal submatrices are positive definite. And if A is positive semi-definite, then all principal submatrices are positive semi-definite. Here we can also use range. If A is positive definite, then its numerical range is on positive real, and all numerical range of all the principal submatrices is included in numerical range of A. So it is also on positive real axis. So all the principal submatrices are then also positive definite. And if it is positive semi-definite, then all the principal submatrices are positive semi-definite. Otherwise, we can directly prove this in this manner. Now, this theorem, let A belonging to Mn be Hermitian. Then A is positive definite if and only if eigenvalues are all positive. And if we take positive, eigenvalues are all non-negative. A belonging to N be Hermitian. If A definite, then X star AX is greater than 0. And we can choose X to be eigenvector, and from this we see for X to be Y, and Y is eigenvector correspond to lambda star Y. So this Y star Y greater than 0 implies lambda Y star Y is greater than 0. Lambda is greater than 0. That is positive definite, then eigenvalues are positive. Now converse part. Suppose A is Hermitian and let all its eigenvalues be positive. Since A is Hermitian, it is normal matrix, and we know our normal matrices are unitarily diagonalizable. So we can write U star AU is equal to lambda, where lambda is equal to diagonal lambda 1, lambda 2, lambda. A is equal to U delta a lambda U star, because here we multiply in by U also here, and in right by U star also here. So A can be written as AU lambda U star. Now take X to be any non-zero vector, then X star AX comes out to be X star U lambda U star X. Now put this U star X is equal to Y. Then X star U, it taking conjugate transpose both sides, we get X star is equal to Y star. So this equal Y star, this lambda Y. Now put value of this matrix lambda Y star, this diagonal matrix Y. And now take of y as y is a column vector, y1, y2 up to yn. Then we calculate mod y1 square plus on up to lambda n mod yn square. Since all eigenvalues are strictly greater than 0 and at least one of y1, y2 is known 0, therefore this is strictly greater than 0. So A is positive definite. This means positive definite means A is Hermitian and its eigenvalues are all positive. Correct? Next theorem, a positive semi-definite matrix is positive definite if and only if it is non-singular. Suppose a matrix is positive semi-definite and it is also non-singular. It is positive semi-definite and also non-singular. This means eigenvalues are not, any eigenvalue is not equal to 0.
0.
So if eigenvalue is not equal to 0 and also matrix is positive semi-definite, so eigenvalues are all positive, so matrix is going to be positive definite. Conversely, if matrix is positive definite, all its eigenvalues are greater than 0, its determinant is greater than 0, so it is non-singular. Clear this theorem?
Yes, sir. Yes.
So yes, this example, Ax is not equal to 0. It may happen that Ax is not equal to 0 vector, but x star Ax is equal to 0. Let x belongs to C2 and A this matrix 1, 0, 0, minus 1. Then we calculate x star Ax. This comes out to be mod x1 square minus mod x2 square. So if we take here mod x1 is equal to mod x2, then x star Ax is 0. For example, we take x to be this column vector 1, 1. Then Ax is this column vector 1, minus 1, which is not a 0 vector. But we calculate x star Ax, this 1, 1, 1, minus 1, this comes out to be 0. Now next theorem, let A is equal to Aij belongs to Mn be positive definite, positive semi-definite, and x be a column vector. Then x star Ax is equal to 0 if and only if Ax is equal to 0. Note that if Ax is 0, then clearly x star Ax is 0. Now converse part, x star Ax is 0, then x is eigenvector, that is then Ax is also 0 vector. In the exercise yesterday we have shown that x star Ax is equal to smallest or largest equal to smallest or largest eigenvalue if and only if x is eigenvector. So if A is positive semi-definite and x star Ax is equal to 0, this means x star Ax is equal to its smallest eigenvalue. Then this means x is eigenvector. That is, then Ax is equal to 0. Otherwise, we can directly prove this. Now, we are going to discuss Sylvester criteria to check positive semi-definite and positive definite, when a matrix is positive semi-definite and when it is positive definite. Now suppose we have this equation, x cube plus x square plus x plus 1 is equal to 0. Yes, this equation has no positive root. Why? Because if it has one positive root, then this sum comes out to be strictly greater than 0. Now, if we change x to minus x and multiply by minus, we get this equation, x cube minus x square plus x minus 1 is equal to 0. So this, if this equation has no positive root, this means this equation has no negative root. Hear this?
Yes, sir.
In general, if the coefficient of the polynomial are alternatively positive and negative, then the polynomial has no negative root. We can write polynomial in this form: x raised to the power n minus a1 x raised to the power n minus 1 plus so on up to this last minus 1 raised to the power n a n. ai is greater than equal to 0 if sum of ais are 0. We can consider them either positive or negative. For example, if a coefficient is 0, then still this holds that this equation has no negative, no positive root. Now, for example, if n is odd, then we can write f of minus x is equal to minus x power n. N is odd, therefore take minus outside. Here it remains as it is. So we can take minus outside, and inside we have this polynomial. Now this has no positive root because all the coefficients are non-negative. So this polynomial has no negative root because this polynomial has no positive root. Also, if n is even, then f of minus x simply becomes x raised to the power n plus a1 this up to an. All the coefficients are non-negative. So f of minus x has no positive root and hence fx has no negative root. Clear this?
Yes, sir.
Let A belongs to Mn. Eka denoted by Ekk the sum of the principal. There are principal minor of size k. The total number of principal minor of size k is nck. For equal to 1, we have principal submatrices of order 1, that is all the diagonal entries. We have n principal subminors. Now, if we denote Eka, the sum of principal minors of size k, then its characteristic polynomial can be written in this form: lambda raised to the power n minus e1a lambda raised to the power n minus 1 plus e2a lambda raised to the power n minus 2 plus so on up to minus 1 raised to the power n en a. E1a we have defined, this is also sum of eigenvalues. ena product of eigenvalues. E2a sum of the product of
Eigen taken to it.
E3 sum of the product of eigenvalue taken 3 at a time. Hear this.
Yes, sir.
Also, to discuss Sylvester criteria, we also need Cauchy interval principle. This says that if B belonging to Mn be Hermitian and Y belongs to Cn and X is any real number, then this matrix B has order n, and we have bordered it. We
Hello.
Recording in progress.
Yes, now I am audible. I am audible.
Yes, sir.
Connection खराब हो गया था.
Yes, sir.
Yes, now visible I am. Okay, this screen is visible.
Not visible, sir. But voice is audible.
दोबारा शेयर यार उसको बुला लो, वो मर गया कहीं जाके टाइम. ये 10 मिनट से कम टाइम पे. Yes, visible now.
Yes, sir.
So this Cauchy interlacing principle, this is clear.
Yes, sir.
Eigenvalues are arranged as lambda 1b less than equal to recording. Lambda 2b less than equal to so on lambda n b. And then lambda 1a less than equal to lambda 1b less than equal to lambda 2a so on up to lambda nb less than equal to lambda n plus 1a. Clear this Cauchy interlacing principle. If eigenvalues of B are arranged in ascending order, then the smallest eigenvalue of A is less than equal to lambda 1b and so on, and largest is greater than equal to lambda nb. And in this way, the eigenvalues of A are placed in between. Now, Sylvester criteria, A-B Hermitian. If every principal minor of A is non-negative, then A is positive semi-definite. If every leading principal minor of A is positive, then A is positive definite. Clear? In the third part, it is what are the leading principal submatrix? These are on the this left. Say this first A11. This is first leading principal submatrix. Then take this principal submatrix. This is second leading principal submatrix, and then take this third one. So all these are leading principal submatrix. Statement is clear?
Yes, sir.
Now let A belonging to Mn be Hermitian and let every principal minor of A be non-negative. As we have discussed, its characteristic polynomial can be written in this form. So where Ek A is the sum of the principal minors of A of size K. Now suppose matrix is non-singular, then what we have here? E1A non-negative, E2A non-negative, ENA non-negative. So all the coefficients are non-negative here. So as discussed above, all its eigenvalues are non-negative. Why? Because A is Hermitian. All its eigenvalues are real. But coefficients are alternatively positive and negative. So none of the eigenvalue is negative. So from here we see that A is positive semi-definite. Also, we can see here if the rank is K or R and R is strictly less than N, then instead of this equation, we will have this equation. This gives all the eigenvalues 0. And from here, all the eigenvalues are again non-negative on using same argument. Again, matrix A is positive semi-definite. Now take second. If all the leading principal submatrices are positive, principal minors are positive, then A is positive definite. We prove this by induction. For A1 is equal to A11, determinant A1 greater than 0, then A11 is greater than 0. So A is positive definite.
Definite.
Suppose theorem is true for K12 up to n minus 1.
1.
Then if all the leading principal minors of AK are positive, then AK is positive definite.
Definite.
Since AK is positive definite, therefore lambda I AK is greater than 0 for all I12 up to K. Now consider this matrix AK plus 1. AK plus 1 is obtained from AK by bordering it. So we can use Cauchy interlacing principle. This is clear how we obtain this by bordering this. Suppose this is 2 by 2 matrix. The next principal, leading principal submatrix is obtained by putting values on the border of this. So this is this matrix. So we can use Cauchy interlacing theorem. So lambda 1 of AK plus 1 less than equal to lambda 1 of AK, so on up to lambda K of AK less than equal to lambda K plus 1, AK plus 1.
1.
From 5 and 6. Because from 5 lambda 1 AK is greater than 0. Therefore lambda 2 of AK plus 1 is greater than 0 up to lambda K plus 1 of AK plus 1 greater than 0. So their product lambda 2, lambda 3 up to lambda K plus 1 of AK plus 1 is also greater than 0. Also given that determinant of AK plus 1 is greater than 0. Therefore, this product starting from lambda 1, lambda 2 up to lambda K plus 1 is greater than 0. Now divide 8 by 7, we see that lambda 1 is also positive. So matrix is Hermitian and all its eigenvalues are positive. Therefore, AK plus 1 is positive definite.
Definite.
So the result follows from mathematical induction, and this is known as Sylvester criteria. Also, if determinant of A is given to be greater than equal to 0, then one of the eigenvalue may be 0. So in this case, we say that A is positive semi-definite.
Semi-definite.
Also note that if all principal minors are positive, then A is positive definite.
Definite.
But it is short to calculate only the leading principal minors. Now next is Lunar partial order. Now eigenvalues of Hermitian matrices are real, so there is analogy between Hermitian matrices and real matrices. Also, the eigenvalues of positive semi-definite matrices are non-negative. So there is analogy between positive semi-definite matrices and non-negative real number.
Real.
This suggests an order relation between matrices. Let A be belonging to Mn, A, B are Hermitian, then and let this be positive semi-definite. A minus B positive semi-definite, A and B are Hermitian. Then we write A is greater than equal to B.
B.
If A and B are Hermitian and A minus B is positive semi-definite, then we write A is strictly greater than B.
B.
Clear this?
Yes, sir.
In this way, if A is Hermitian and positive semi-definite, then A is greater than, we can write A greater than equal to 0 if A is positive definite. In short, we can write A is strictly greater than
0.
For n is equal to 1, this is total order. But for n greater than equal to 1, there are matrices for which neither A is greater than equal to B nor B is greater than equal to A. For example, we have this matrix A and this matrix B. Then A minus B is 1 minus 1, 0, 0. This is neither greater than 0 nor less than 0 because this is not a positive semi-definite matrix. Also B minus A, this is not a positive semi-definite matrix. So the order relation defined above is a partial order. Partial order mean does not hold all matrices, but there are Hermitian matrices for which this order holds. And it is called Lunar partial order. Now this lemma which we will use for next result, if H is Hermitian and X star Hx is 0 for all X belongs to Cn, then H is equal to 0. This is simple. Also we can argue from the numerical range point of view. If X star Hx is 0 for all X belongs to Cn, then H is a scalar matrix. So also it is Hermitian.
So all its
eigenvalues are 0.
0. So all it
must be a 0 matrix because it is a diagonalizable matrix and similar to 0 matrix, and the 0 matrix is similar to itself only. The above lemma in fact valid for all H belongs to Mn. Now this theorem, let A be belonging to Mn be Hermitian, then A greater than equal to B and B greater than equal to A if and only if A is equal to B. If A is greater than if A is equal to B, then we can write these two. Now the converse part. Suppose A greater than equal to B, B greater than equal to A. Then by definition, A minus B and B minus A are positive semi-definite. So X star A minus BX is non-negative real number. X star B minus AX is also non-negative real number. We can take also minus outside. So this means X star A minus BX is both negative and positive. So this must be 0. And this is 0. This implies A minus B is 0 by above. So yes. A is equal to B. Now, in case of real, if X is greater than equal to Y and X is not equal to Y, then X is strictly greater than Y. But in matrices, this does not hold good. Let A be this matrix, B this matrix. Then A minus B is 0, 0, 0, 1. And this is positive semi-definite. But clearly, A is not equal to B. Also, it is not true that A is strictly greater than B. Because for A to be strictly greater than B, we need A minus B strictly greater than 0 matrix. Clear this?
Yes, sir. Yes, sir.
Let A belonging to Mn be Hermitian and let lambda minimum, lambda maximum be its smallest and largest eigenvalue. And lambda maximum of AI is greater than equal to A. And this is greater than equal to lambda minimum of I. That is, in Hermitian matrix, A is less than equal to lambda maximum time identity matrix. A belonging to Mn be Hermitian. Let lambda 1, lambda 2, lambda n be eigenvalues of A. By spectral theorem, there exists a unitary U such that U star AU is equal to this
diagonal matrix.
Then we can write, as we have already discussed, A in this form. If X is any unit vector, then this can be written as X star U diagonal this U star X. Now put Y is equal to U star X, we have this expression, and then on calculating, we have this convex combination of eigenvalue.
Yes, sir.
And we know this convex combination of eigenvalues lies between minimum and largest eigenvalue. So this is true. Now here multiply with X star X because X star X is 1. So take common, we have X star lambda maximum AI minus AX is non-negative. And also X star A minus lambda I X is non-negative for all X belongs to C. And we have taken this to be unit vector. We can also divide both sides by X star X. So this is true for all X belongs to Cn. And what is it? This is the definition of positive semi-definite matrices. So lambda maximum AI here is greater than equal to A. And A is less greater than equal to lambda minimum AI. Clear this?
Yes, sir.
Now let A belongs to Mn. Then I identity is greater than equal to A if and only if lambda maximum is less than equal to 1. Also for strict inequality, we have lambda maximum less than 1. Now A is Hermitian, therefore unitarily diagonalizable. Also A is positive definite. We have studied this. X star AX is positive semi-definite. So I minus A greater than equal to 0. This holds if and only if X star of I minus AX, here X is unitary. Now take this inside U star U identity minus U star AU is greater than equal to 0. This holds if and only if we write it in expanded form, and this matrix is this. This is positive semi-definite, and all the diagonal entries must be non-negative real numbers. So 1 minus lambda I greater than equal to 0, and this means lambda I is less than equal to 1. And this also if and only if lambda maximum is less than equal to 1. Clear this?
Yes, sir.
Now we define this matrix, for example, under root a to the power 1 by 2, 1 by 3, etc. when A is positive semi-definite. Let A belonging to Mn be positive semi-definite and its eigenvalue, these are all non-negative. Now, every non-negative real number has a unique non-negative kth root. So if we have this diagonal matrix, then we define D to the power 1 by k as diagonal. Take kth root of each diagonal entry here. This is matrix D to the power k.
K.
Now, by spectral theorem, A is unitarily diagonalizable. So U star AU is equal to D, this diagonal matrix. From here, we have A is equal to U diagonal lambda 1, lambda 2, lambda and U star.
Star.
So every Hermitian matrix can be defined like this. So we can define A to the power 1 by k as this matrix. A to the power 1 by k is equal to U D to the power 1 by k U star. Say this B. Also note that B raised to the power k is equal to A. For example, if we have A half is equal to this, U D half U star, then P square is U D half U star U D half U star. U star U is identity. So this is U D U star, and this is A.
A.
This defines A to the power 1 by k. Now we also have spectral radius. Let A belongs to Mn. The spectral radius of A is the radius of the smallest disk centered at origin, which contains all the eigenvalues of A.
Matrices.
This means rho A is maximum of the modulus of the eigenvalues. Lambda belongs to sigma A means lambda is in the spectrum of A.
A.
Now we have this theorem. If A is Hermitian, A we take to be positive definite and B positive semi-definite, then A is greater than equal to B if and only if rho A inverse B is less than equal to 1. And if we have strict inequality here, we have strict inequality. Now A is greater than B, then for every non-singular matrix S star A minus BS is also strictly greater than 0. That is, this is positive definite matrix. Now take S to be A minus half, S star to be A minus half, star is equal to A minus. Now from 1, A greater than B. This means A power minus half, A minus half, this greater than A minus half, B A minus half here. This means identity is strictly greater than A minus half, B A minus half. This, and as proved above in A result, then 1 is greater than largest eigenvalue of this. This means 1 is greater than lambda maximum of A inverse B. Why? Because eigenvalues of xy are same as eigenvalue of yx. So we can bring this A minus half to this side, then this A inverse B. And what is this? Rho A inverse B. 1 is greater than rho inverse B. Now this is also important. If A belonging to Mn is Hermitian and A and B are positive definite, then A is greater than equal to B if and only if B inverse is greater than equal to A inverse. We know if A is positive definite and B is positive semi-definite, then as proved above, rho A inverse B is less than equal to 1.
1.
Now, if both are positive definite, we can apply this to B inverse and A inverse. In place of A, we have B inverse. So this is B inverse inverse. And in place of B, we have A inverse. This is less than equal to 1. So rho of B A inverse is less than equal to 1. This means rho of A inverse B less than equal to 1. Clear this? And what does this mean? This means this is true. That is, B inverse is greater than equal to A
Inverse.
This is true by these two. Now we come to positive linear maps. Have you studied before positive linear maps? Participants, anyone?
Yes, sir.
Any other? Sakshi? Ravinder?
Yes, sir.
Hitesh?
No, sir.
Okay. Let Mn denote the set of all n by n complex matrices and let A belongs to Mn. A map phi Mn to Mk is called linear if for every AB belonging to Mn and C any complex number, we have phi of Ca plus B is equal to C phi A plus phi B. Then this is a linear map. And a linear map is called positive if phi A is positive semi-definite matrix whenever A is positive semi-definite. And it is called unital if phi of In is equal to Ik, because this map is going from Mn to Mk. So identity goes to Ik. If these three are satisfied by a map from Mn to Mk, we say that this capital phi is a positive unital linear map. In the special case, when we take K to be 1, that is here we have K1, that is this is 1 by 1 matrix. Then phi is a map from Mn to complex numbers. Then this particular case is called positive unital linear function. And we denote it by this small letter phi. Now, examples of positive linear maps. Take this first example, phi A is equal to trace A. This is a positive linear functional. Linearity follows from the fact that trace functions are linear function. So phi is linear. Also, if A is positive semi-definite, then all the diagonal entries and phi A is equal to trace A is non-negative. So phi A is equal to trace A is non-negative. So phi is positive. But if we take A to be identity matrix, then trace of identity is n. So A is not unital here. But if we define map like this, phi Mn to C as phi A is equal to trace A by n, then this is a positive unital linear function. Positivity and this linearity follows as above in case of phi A is equal to trace A. And why it is unital? Because in this case, trace of, if we take A to be identity, then trace of identity is n divided by n. This comes out to be 1. So phi A is equal to trace A by n is positive unital linear function. The map defined by phi A is equal to A transpose is a positive unital linear map, where A transpose denotes the transpose of A. Now phi of CA plus B, it is linear. CA plus B transpose, this is equal CA transpose plus B transpose. This is phi A plus phi B and C here. So phi is linear. Also, if we take A to be positive semi-definite, then we have studied just A transpose is also positive semi-definite. So phi A is equal to A transpose is positive semi-definite, and hence phi is positive. Also, if we take A to be identity, then its transpose is also identity. So phi is also unital. So phi A is equal to A transpose is positive unital linear map. Let phi mn to mk. Next example defined like this: x star ax, where x belongs to mn k. Then phi is again positive linear map. Linearity follows because we can write this as C x star ax plus x star bx, which is C phi a plus phi b. So phi is linear. Now positivity follows. We have just proved that if A is positive semi-definite, then x star ax is also positive semi-definite. So phi a is equal to x star ax is positive semi-definite, hence phi is positive. Now phi of identity, if we put A is equal to identity here, we have x star x. This need not be identity. So phi is not unital. Now let, instead of x, we take U to be unitary matrix. Then this map Mn to Mn defined as phi A is equal to U star AU is a positive unital linear map. Positivity and linearity is just same as here. Phi is equal to x star ax, and why it is unital? Because when A is identity, we have here U star U, which is again identity. So phi is positive unital linear map. Now the compression map that takes an n by n matrix A to a k by k block AK in its top left corner is also a positive unital linear map. That is phi mn to mk defined like this: phi A is equal to AK. AK you can think of is the leading principal submatrix of order K, where K is less than equal to n. Linearity follows because phi of CA plus B leading principal submatrix of CA plus B of order K. Then this equals CAK plus BK, this remains C phi A plus phi B. So phi is linear. Now let A be positive semi-definite. Then all its leading principal minors are non-negative. This we have studied. Also, all principal submatrices of A are positive semi-definite. So phi A is equal to AK is positive semi-definite, and hence phi is positive. Now this lemma, A belongs to Mn is Hermitian. If and only if it can be written as A is equal to A plus minus A minus. Each of A and A minus is positive semi-definite matrix. Why? Let A be Hermitian and these are eigenvalue. This diagonal matrix, then there exists unitary U such that A is equal to UD U star. That this we have studied several times. Now we write D plus as this diagonal matrix, lambda 1 plus lambda 2 plus lambda n plus. And what are these plus? Maximum of lambda I 0. That is, if lambda I is greater than 0, we write here lambda I. If lambda I is negative, we write here 0. Likewise in D minus, if minimum of lambda I 0. If lambda I is negative, we write negative, otherwise 0. And then D plus minus D minus is D. And also D plus is positive semi-definite, D minus is positive semi-definite. What we are doing, suppose we have this matrix. Then write it like in this manner: 1, 1, here minus 2 is negative, so write 0. 3 is positive, like this. In place of minus 4, write 0. And here 1 is positive, so write 0. And this minus 2, taking minus outside. This again 3 is positive, so write 0, and minus 4, take minus outside, write this. So these two both are diagonal matrix and both are not that positive semi-definite, as their diagonal entries are non-negative. So now A is equal to UD U star. We are writing D as D plus minus D minus. D plus minus D minus. And what is this? This is just A plus. And this is A minus. So these are positive semi-definite matrix. Converse is simple. If A is this, then A plus A and A minus. If these are positive semi-definite, then take conjugate transpose. This comes out to be same as A. So A is Hermitian matrix. Now every positive linear map is adjoint preserving. That is phi of T star is equal to phi T star. This means linear map is adjoint preserving because phi of conjugate transpose of matrix is equal to phi of A and then taking conjugate transpose. Now we use this last lemma to prove this result. First we show that phi A is Hermitian if A is Hermitian. By lemma 1 we have A is equal to A plus minus A minus, where A plus minus are positive semi-definite matrix. On applying phi and use the linearity of phi, we have phi of A is equal to phi of A plus minus phi of A minus. Now here A plus and A minus are positive semi-definite and phi is positive unital linear map. So phi A plus by definition is also positive semi-definite, phi A minus is also positive semi-definite. So this is the difference of two positive semi-definite matrices and hence is Hermitian. Because this is then difference of two Hermitian matrices, which is Hermitian. Now take general case. Now every matrix T can be written in this form: A plus iota B, where A and B are Hermitian. Here A is T plus T star by 2 and B is T minus T star by 2 iota. Now take phi T whole conjugate. This equal, write T as A plus iota B. So phi A plus iota B whole conjugate transpose. Use linearity of phi here. This is phi A plus iota phi B, then star. This is phi A star plus iota phi B star. This comes out to be minus iota phi B. Again, by linearity, we can take phi outside. So this is A minus iota B. So phi T star. So from here, we see that every positive unital linear map is adjoint preserving. That is phi T of whole star is same as phi of T star. Now in next theorems, we also use the concept of tensor product. The tensor product of a matrix Aij belonging to MMN, that is of order M by N, and Bij is a matrix of order P by Q. Then A cross B is defined as, that is a tensor product B is defined as Aij, that is multiplying each entry by scale this by the matrix B. This acts like as scalar product inside bracket. So we get a matrix of order MP and Q. For example, this matrix A and this matrix B. Then tensor product is multiplying each entry here by B. 1B, 4B, 9B, 2B, 5B, 9, 3B. This is then tensor product of A cross B. Now again, next we have to use scalar multiplication, that is multiplying B by 1. So we have 3, 4, 2, 1 here. Then 4B, 12, 16, 8, 4, this here, and so on. And B tensor product A comes out to be this matrix. So in general, tensor product A B is not equal to tensor product B A. Now we use this lemma also in next theorem. If AB are Hermitian, then their tensor product is also Hermitian. This is simple to check. A cross B star. A cross B mean A tensor product B. This by definition is this matrix multiplying each entry of matrix A by B. This conjugate transpose here as it is. Now taking conjugate transpose, this will become this matrix A11 conjugate B star, A21 conjugate B star, so on. And so by definition, this matrix is tensor product of this matrix with B star. And this is A conjugate. A conjugate tensor product B conjugate. So this equals A conjugate by because A star is A, B star is B. So if A and B are Hermitian, then A tensor product B is also Hermitian. Now in this lemma, we show that if A and B are square matrices, then the eigenvalues of A tensor product B are obtained on multiplying eigenvalues of A and B pairwise. That is, if eigenvalues of A are lambda 1, lambda 2, lambda n, and eigenvalues of B are mu 1, mu 2, mu n, m. Then eigenvalues of A tensor product B is lambda 1, mu 1, lambda 1, mu 2, so on up to lambda n, mu m. And what is the proof? Since lambda is eigenvalue of A, we take x to be eigenvector, so we have this equation. Likewise, for B, if mu is eigenvalue, we have this equation, by is equal to mu y. Now consider this, A tensor product B, x tensor product y. On using partition multiplication, we see that this equal AX tensor product BY. Now AX is lambda x, BY is mu y. So this equal lambda mu x tensor product y. So this means x tensor product y is eigenvector and lambda mu is eigenvalue. From this, it is also clear that if A and B are both positive semi-definite, then tensor product is also positive semi-definite, because we have already shown that if A and B are Hermitian, A tensor product B is also Hermitian. Also, their eigenvalues are obtained on multiplying eigenvalues of A and B. So if eigenvalues of A and B are non-negative, eigenvalues of A tensor product B are also non-negative. So A tensor product B is positive semi-definite. Now we discuss this proof of this Carrichon inequality, 1952. Let phi mn to mk be a positive unital linear map. Then for any Hermitian element A belonging to mn, we have this inequality. Phi of A square is greater than or equal to phi A whole square. Now let lambda 1, lambda 2, lambda n be the eigenvalues of A. Phi spectral theorem, this we have discussed in first lecture on first day. A can be written as lambda 1 p1 plus lambda 2 p2 plus lambda n pn, where pi's are corresponding projections. That is, they are idempotent matrix, they are also Hermitian, also positive semi-definite, also orthogonality is satisfied. Pi pj is equal to 0 matrix, I not equal to j. And sum of all these pi is equal to identity matrix. Now apply phi to both sides of A and use linearity. Phi A become phi of this lambda 1 p1 plus lambda 2 p2 plus lambda n pn. Now phi is linear. So this equal phi of lambda 1 p1 plus phi of lambda 2 p2 plus so on. Also we can take lambda 1 lambda 2 outside. So phi A can be written as lambda 1 phi 1 plus lambda 2 phi 2 plus so on up to lambda n phi n. Also apply phi here both sides. Phi of identity is identity. And again use linearity. This equal phi p1 plus phi p2 plus so on up to phi pn. And similarly, what is phi A square then? A square can be written as here lambda 1 square p1 plus lambda 2 square p2 plus so on up to lambda n square pn. So on applying phi, we have phi A square is equal to this expression. Now note that this matrix is positive semi-definite. Why? This is Hermitian because eigenvalues lambda I are real. Also note that diagonal entries are both non-negative. and determinant is 0. So this is positive semi-definite matrix. Also, each pi is positive and phi is positive unital linear map, so phi pi is non-negative. Now use the fact as we have discussed just tensor product of two positive semi-definite matrices is positive semi-definite. So this tensor product lambda is square lambda I1 tensor product phi pi greater than equal to 0. Now since these matrices are positive semi-definite, their sum is also positive semi-definite. So this gives sum I1 to n, this matrix positive semi-definite, and so we have taken the tensor product. Tensor product means each entry here is multiplied with phi pi, phi pi, phi pi. This is scalar multiplication here. Now, sum of matrices is obtained by adding entries of each matrices. So this matrix is positive semi-definite. Now this is phi of a square, this is phi of a, this is phi of a, and this is identity. So we have this matrix is positive semi-definite. Now use this fact. If a matrix B is positive semi-definite, then X star Bx is also positive semi-definite. And choose X to be this matrix. Then we calculate that X star Bx comes out to be this matrix. And this is positive semi-definite. Every principal symmetric, so positive semi-definite matrix is positive semi-definite. So from here we get phi a square is greater than equal to phi a whole square. Clear this inequality?
Yes, sir.
A related inequality is choice inequality. This says that if phi mn to mk, we take here to be this strictly positive unital linear map. Here it is strictly positive unital linear map. Then for every positive definite matrix A, we have this inequality. Phi of A inverse is greater than equal to phi A whole inverse. Phi is strictly positive mean if this phi A inverse is also positive definite, and this phi A inverse is also positive definite. Again, similar type of proof, lambda is our eigenvalues of A. Then by spectral theorem, we can write A in this form, where Pi's are projections. And then phi A is equal to lambda 1 phi P1 plus lambda 2 phi P2 up to lambda n phi Pn. Also, then phi P1 plus phi P2 plus phi Pn is equal to identity. Also, A inverse eigenvalue of A inverse are lambda 1 inverse, lambda 2 inverse, n inverse. So we can write A inverse in this form. Now again apply phi to this, and using same argument as above, we have phi A inverse, phi A identity, this equal tensor product of these two matrices. Now both are positive semi-definite because here eigenvalues are positive and determinant is non-negative. So this is also positive semi-definite. So if again use this argument B is positive semi-definite, then X star Bx is also positive semi-definite. And choose X to be this matrix. We have this matrix comes out to be positive semi-definite. So again from here, this is principal submatrix. So phi A is greater than equal to phi A inverse. But we have just studied that if phi A is greater than equal to, if A is greater than equal to B, then B inverse is greater than equal to A inverse. This means inverse of this, which is phi A inverse, is greater than equal to inverse of this, which is phi A whole inverse. Now Choi has one more theorem. This is the extension of Carrichon theorem for normal matrices. Let phi mn to mk be a positive unital linear map. Then for every normal element A belonging to Mn, we have phi A star A is greater than or equal to phi A star. And we can also interchange these two. That is, this is greater than or equal to phi A star phi A. Proof is similar as of above theorem. Here we can write, if A is normal, we can write this A in this form. And A star is then lambda 1 conjugate P1 plus lambda 2 conjugate P2 up to lambda n conjugate Pn. Then from here we have A star A is equal to mod lambda 1 square P1. Why? Because when we multiply these two, P1 square remains P1. And this is mod lambda 1 square. But when this is multiplied with this, P1, P2 is 0. P1, Pn is also 0. Likewise for other terms. So we have this expression. And we calculate as above. This comes out that phi of A star A, phi A star I is equal to sum this tensor product this. Again, these are positive semi-definite matrices. This is positive semi-definite because this lambda I, here we have its conjugate. Diagonal entries are non-negative and determinant is 0. Now, so this matrix is positive semi-definite. Again, choose X, this matrix, and use this fact. P is positive semi-definite, then X star Bx is also positive semi-definite. We calculate that this matrix comes out to be positive semi-definite. This gives 5. The inequality, next inequality, this follows on using similar arguments. Now we discuss what is the motivation or background of this Carrichon and theorem and Choi's inequality. These Carrichon theorem and Choi inequality are known as the non-commutative versions of Cauchy-Schwarz inequality. We discuss it how it is non-commutative version of Cauchy inequality. Now, Cauchy inequality for numbers, this is proved by Cauchy in 1821. Xi and yi, we take real numbers. Then Cauchy inequality says that some xi yi whole square less than or equal to some xi square, some yi square. This Cauchy inequality for real number also has complex analog. This says that if we have complex number zi and wi, then mod some zi wi whole square less than or equal to some mod zi square, some mod wi square. Also note that w modulus of a complex number and its conjugate are same. So here we can also denote, also write in place of wi conjugate. Here it right hand side expression remains same because here we get modulus of wi conjugate, which is same as modulus of wi. Now there are a number of proofs of this Cauchy-Schwarz inequality in literature. Cauchy himself derived this inequality on using this Lagrange identity. Now a quick proof of Cauchy inequality also follows on using properties of positive semi-definite matrices. Consider this matrix, first matrix. Diagonal entries are real and also non-negative because modulus are involved. Also this A12 entry Z1W1, this is a complex number, here it's conjugate. So this is Hermitian. Also its determinant is 0. So this is a positive semi-definite matrix. In this way, all other matrices are positive semi-definite. And sum of positive semi-definite matrices is positive semi-definite. So this matrix comes out to be positive semi-definite. Now put its determinant greater than or equal to 0. We get Cauchy inequality in complex form. Now Cauchy inequality in matrix algebra. Mn, we have noted the algebra of all complex n by n matrix and let A be any n by n matrix. Take its entries as Aij. then we know trace A is sum of diagonal entries. If we take another matrix B with entries Bij, then the entries of this product AB are AB I jth entry. This equals AI1 B1j plus on up to AIN B and J. And likewise that of product BA, the ijth entry of product BA can be written like this. So in general, AB is not equal to BA. Now, from this, we can calculate trace of AB and trace of BA. Just putting here j is equal to I and taking sum I1 to n. Trace AB comes out to be sum ij1 to n aij bji. And this also equals sum ij1 to n bij aji, which is trace B. So trace AB, this also gives the proof that trace AB is same as trace B. Now from this calculate trace A star. In place of B, write A star. So this becomes sum ij mod aij square. Why? Because then bji is entry of A star, which is then aij conjugate. So aij into aij conjugate is mod aij square. Similarly, trace BV star is this expression. Now from Cauchy inequality 2. Now we have these n square numbers. This mod aij, I varies from 1 to n, j varies from 1 to n, so n square number. So this we have applied Cauchy inequality to n square number, and we can write this expression. Now left hand side, as shown here, is trace AB mod square, and right hand side is trace A star, and this is trace BV star, where A star denotes the conjugate transpose of A. It is also clear that we can also write this in this form, trace AB star, because this equal trace A star, then trace B star B, which is same as trace BB star. Now the proof of this inequality for traces. Note that this inequality for traces, the proof depends on the Cauchy inequality for numbers. This proof of this also follows from general Squarge inequality, Cauchy Squarge inequality in inner product space. In inner product space, if U and V are any two vectors in V, then modulus of inner product UV square is less than equal to norm U square norm V square. Where norm U square mean inner product U with V, U. And similarly, norm V square is V inner product V. The inequality 4 is known as Cauchy-Squarge inequality. Now, this set Mn of all complex n by n matrices is a vector space and is inner product space with inner product defined like this. This inner product AB trace AB star trace B star A. The Squarge inequality 4 then follows from implies this inequality. Why? Here we have trace AB star mod square, and this is trace A star, this is trace BB star. Now positive unital linear function, we have discussed these in detail. These are also examples of positive unital linear functional. Now every linear functional on a finite dimensional inner product space is an inner product with a fixed vector in that space. So, and we have that Mn is inner product space and inner product defined like this, trace AB star. So phi A can be written as trace AB star. So in place of B star, we just denote it by X. So phi A is equal to trace AX for some fixed X in Mn. Further, phi A is positive if and only if X is positive. See this book by Bhatia, 2007. The book Positive Definite Matrix by Bhatia is Very useful for studying this topic. Yes, someone is asking. Also, phi is unital if trace of x is equal to 1. That is, if this phi is positive unital linear functional, if and only if x is positive semi-definite matrix. And also it is unital when trace of x is 1. Positive matrices, that is positive semi-definite matrix with trace 1, are called density matrix in physics literature. We now show the extension of this inequality for traces for linear function. That is, if phi is a positive unital linear functional, then phi of AB star mod square is less than equal to phi of A star, phi BB star. Begin with this equal trace AB star x. Because as we have shown here, this phi A can be written as trace A x. So this is trace AB star x. And we can write then this as take A to this side, because trace of xy is same as trace of yx. Now here x is positive semi-definite. Why? Because phi is positive unital linear map. So we can write this as b star. In place of x, write x half, x half. Now use Cauchy inequality for traces to these two. Take this as one matrix b star x half and x half A as second matrix. So this is less than equal to this expression. Now this expression simplifies to trace BB star x, trace A star x. And these are phi BB star, phi AA star. So this inequality for functional also depends upon inequality for numbers. Now positive unital linear maps that we have studied these in details. Carrichon inequality we have proved. We are now going to discuss why this is non-commutative version of Cauchy-Schwarz inequality. This depends upon the Cauchy inequality for numbers. If we take here B to be identity and A Hermitian matrix, we have this inequality for functional. And what is Carrichon inequality? In place of functional, we have this positive linear map. Again, and this is the non-commutative version of Cauchy-Schwarz inequality. Why? Again, if here phi A and phi A square commute, then we can reduce the inequality to the real valued case, and proof follows as same as in case of numbers. Why? Because if A is Hermitian, then for any real number alpha, A minus alpha E whole square is positive semi-definite matrix. And expand this, we have A square minus 2 alpha plus alpha square I is positive semi-definite. Now apply phi, and using linearity, we have this inequality. Also, we use same result. If A is positive semi-definite, then x star AX is also positive semi-definite for all x belongs to MN. Now, therefore, for any unitary, this matrix is positive semi-definite. Now, phi A is Hermitian, and we are assuming that it commutes with phi A square. So there is a single unitary matrix U, which we will take both of these matrices to diagonal matrices. So writing this in diagonal form, we have this gamma 1, which is eigenvalue of phi A square, minus 2 alpha beta 1 is eigenvalue of phi A plus alpha square. Similarly, other entries. This is positive semi-definite, and this is true for all real numbers alpha and beta. All real number alpha. So we choose alpha is equal to say beta 1. Then what we have gamma 1 minus beta 1 square greater than equal to 0. So this means gamma 1 is greater than equal to beta 1 square. Similarly, in general, we choose alpha is equal to beta I. We have gamma is greater than equal to beta I square. So we have this inequality. So, and what is this? This is U star phi A square U, and this is U star phi A whole square U. So this implies phi A square is greater than equal to phi A whole square. So if here phi a and phi a square commute, then again this is not a non-commutative version. Why? Because proof follows in a similar way as it follows for numbers. Now, this is the remark given by Carrichon in his paper, that this standard proof does not apply to give simple proof for linear maps. Now we assume that phi a and phi a square do not commute. So then what will happen? He has given this example. Take B this matrix and C this matrix. Then for every real number alpha, B minus 2 alpha C plus alpha square I comes out to be this matrix. This is positive semi-definite. What we are doing in place of this, A square minus 2 alpha I plus alpha square I. He has given this example that this holds. This is positive semi-definite. But B minus C square is this matrix. Determinant of this matrix is 1 minus root 2, which is negative. So this matrix is not positive semi-definite. What Carrichon is saying is that this proof cannot be applied to give simple proof for linear maps when phi a and phi a square do not commute. This means this inequality, Carrichon inequality, is a non-commutative version of Cauchy-Schwarz inequality. Proof of Carrichon inequality we have already discussed. So I think it is enough for this lecture. We'll try some more question in tutorial. Yes, any question from participants?